This is projectile motion with Python programming. This is for Dr. Marbles 2425 University Physics at Tarleton State University. This presentation is by Jordan Cutbirth and
Jeff Carranza.
Our approach to this is to first define the problem, where our origin axes are, define the equations needed for the calculations, determine the Python language used or needed, and once our program is finished, to properly describe our program.
In defining the problem, this is what we expected our results to look like with air drag and without air drag for the height and range components.
In defining our problem, we also needed to determine our origin and our axes that we are intending on using. Initially, we attempted to set the box as the origin and gradually make that larger based off of the range. What we ended up doing, what we ended up having to do, is to actually set our ball as the origin in order to get accurate results, and then we positioned our box based off of that.
And the calculations that we used for this program were the velocity equations with v naught y and v naught x, and for the maximum range and height equations we used height and range.
Again, our program requirements are our program has to have the capability for a user to input values for our variables. This includes our mass, our radius, our launch angle, as well as our initial velocity. Another requirement is that we need a visual representation of the motion, which is actually showing our projectile through the air and giving a trail of its previous motion. Next is we have to be able to have a user input the rate to adjust the speed of the program. That way you can speed up or slow it down to visually determine what our motion is doing. And lastly, print our desired values, which are our calculations.
This is our first part of the program, and with the two on the top left, you can see two imports, which the visual, what it does is let you see the actual program running. And what the math import does is it lets us use math in our equations. Under that is the inputs, which are the inputs needed from the user to calculate the program. And then under that is the parameters of the projectile used, which is the ball, which equals the sphere, equals sphere, which is our shape, and the origin of the ball is x equals 0, y equals 0, and z equals 0. Then it's the radius equals float r, which what float does, it lets us use r as an input for the radius. And then the color is color of the ball is green, which was a requirement. And then the make trail true is a trail left behind the ball while it's in the air. And then these are our constants and variables. We use them in the equations, and velocity equations used in the program also. And then the parameters for time lets the program know when to start and when to take measurements, which is every 0.01 seconds.
This is the second portion of our program. The first section tells the program when to run, so it's saying that it is finished whenever the program is false. Again, beneath that, kind of indented, is our rate, and a float rate allows for the user to input a value that will change how fast the program actually visually runs. Beneath that is our height and range equations, and as you could tell, there is acceleration in the y direction, which is gravity, and no acceleration in the x direction, which is our range. And together we use both of those in the next line. The ball POS is equal to vector range, height, and 0. The range obviously being our x component, the height being our y component, and 0 being our z component. And that's how we came up with our position. Next is our parameters for the box. So the equations for A, B, and C are just equations that are used to center the box every 0.01 seconds, every time it takes a measurement. It'll center the box and elongate the box every time to compensate for the new range of the motion. Again, the parameters of the box are shown. Ground equals box POS. Again, that defines our position, our size in the next portion, and our color. In our last section, tells when the program is finished, and what this says is that if the height is negative 0.0001, which is less than 0, that's whenever our program is finished or is true, and that's when it actually prints the values below. And the green portion that's in the quotations, that's actually the grammar or the letters that the user will see, the words. And then the str is a string function that will actually pick those values up from the program above, and that's what it shoots out. Again, further describing the position of the box. Here is just a further explanation of how we have our box centered, and this obviously shows the box or the ball being at the origin and the box being just below it, and the box is actually positioned off the x-axis. The radius plus 5, because 5 is half the thickness of the box, obviously positioning it in the y direction. And then again, the range is cut in half, and we add 5 on each end in order to position the box in the center of the range plot.
Here's a visual of our project after it's ran. On the left is our program, and on the top right is shows the inputs, which are indented, and under that is the results of the program. And the window under that one is our program after it's ran, and it's it left a trail showing where it went.
Now for air drag. This is what we're expecting our results to look like. We know that it's going to have less height, less range, obviously due to the air drag. So this is what we're expecting.
Again, calculations we used are the same velocity equations and range and height equations, but this time we're also using an air drag equation.
So this is our first attempt at the air drag program. Here we tried to use the same height and range equations from our previous program, but as you can see, the drag force equation set up, we tried to keep those two components separate. Again, factoring in that air drag and then plugging it into that ball position and making the R drag and H drag are new X and Y coordinates. At our second attempt, we tried to calculate the drag force by itself and subtract the two vectors, as you can see in the ball position line. Unfortunately, that was not successful as well, and overall, we were not able to accomplish the air drag and projectile motion. However, we were able to do it without air drag, but we do understand that air drag is a concept or a value that cannot be excluded or taken out of the equation. It is not negligible.